Well, hello. When last we left off, in part 1 of our stoichiometry video, which stopped slightly prematurely at 8 minutes instead of stopping it at 15 minutes, I'm going to get a timekeeping device out for this one. We were talking about the bicycle factory, and we talked about how the first two were ideal and the second one was not ideal, and so we had something that ran out first and we had something in excess. Now, the first part of stoichiometry chapter is really focused on number 1 and number 2 in the bicycle analogy. We're working on ideal stoichiometric calculations. What does that mean? That means we have all ideal ratios, so we don't have any excess. That means no limiting reactants or excess reactants. That means these are very easy, okay? So if you're getting nervous because I'm using big words, stoichiometric, don't be nervous because this is very simple. Okay, here's our first actual real equation. This is the combustion of propane, which I used last night to cook some yummy hamburgers. We'll balance that. Every reaction has to be balanced. That's just going to have to be a standing rule. 3 carbons, 8 hydrogens. 4 times 2 gives me 8 hydrogens. That gives me a total of 10 oxygens on the right. 3 times 2 is 6. 4 times 1 is 4. 6 and 4 make 10. I need 5 oxygens here. Now, let's interpret what this really means. Okay, let's start. I don't like how that covers up my reaction, so I'm going to see if it'll slide down. There we go. Let's start with a sentence. This means 1 molecule of propane reacts with 5 molecules of carbon dioxide to create or make 5 molecules of oxygen to make 3 molecules of carbon dioxide and 4 molecules of water. That's what this tells us. Now, I have a question for you. I'm not going to type it out anymore, okay? I have a question for you. What happens if I have 2 molecules of propane? What if we start with 2 molecules of propane? I'm just going to do it down here below it. What if we had 2 molecules of propane? How much oxygen would we need? Did you say 10? You're correct. How much carbon dioxide would that make? Did you say 6? That's correct. And did you say 8 there? That's correct. So basically doubling the propane doubled everything. See how it's like a recipe? Have you ever had to double or half a recipe or triple a recipe? Now, what if we started with 10 molecules of propane? 10 molecules of propane. Well, then you would need, did you say 50 molecules of oxygen? Did you say 30 molecules of carbon dioxide? Did you say 40 molecules of water? See, I'm just multiplying everything by 10. But the ratio remains the same. What is 10 divided by 2? 5. What is 50 over 10? 5. The ratio between oxygen, propane, carbon dioxide, and water remains the same. So there's something magical about those coefficients. There really is. There really is. What if we do millions? What if we have 1 million propanes? Would that be 5 million oxygen molecules and 3 million carbon dioxides and 4 million waters? Yes, it would. What if I had this many? 6.02 times 10 to the 23rd molecules. Now, if you recognize that that's 1 mole, of molecules, then you have got this figured out. Because if I have 1 mole of molecules, then how many moles of oxygen do I need? Did you say 5 moles of oxygen? And did you say 3 moles of CO2? And did you say 4 moles of water? If you did, you're correct. So what you see now is that the coefficients give us moles. The coefficients equal relative number of moles. This is an extremely important idea, so make sure you commit this idea to memory. that the coefficients give us moles, coefficients give us moles. Hey la, the coefficients give us moles. Yes they do, yes they do. The coefficients give us moles. Yes they do, yes they do. Next page. Alright, here's our first real problem. First, we need to read it. In photosynthesis, carbon dioxide is reacted with water, so I'm just writing the equation. Carbon dioxide is reacted with water to make or create, to produce, to yield glucose and oxygen. Do you remember glucose from biology? There's a biology class happening in Miss Reuter's room right now. Glucose and oxygen. You should remember that oxygen is diatomic. Now, this is an easy one to balance. 6 carbons, 12 hydrogens, 12 hydrogens. Then we already have 6 oxygens, and we need 12 more, so we put a 6 there. Okay? So we have to begin with a balanced equation. So 6 reacts with 6 to make 1 and 6. Now, let's look at number 1. How many moles of CO2 are needed to react with 5 moles of water? Now, a lot of you can do this problem in your head. That's great, but we need to write it out. So we're going to do this the same way we've always done problems. We're going to write what's given. 5 moles of water. Now, if you got slack last chapter and left out the water part and might have just written 5 moles, you cannot do that. You cannot do that. So we're given 5 moles of water to begin with. What's going to go on the bottom of this bracket? Did you say moles of H2O? If you said moles of H2O, you're correct. You're correct. We have to cancel out moles of water. What are we asked to find goes on the top. On the top, what are we asked to find? We're asked to find moles of CO2. So in every stoichiometry problem, you might need to sift through some words and find what you're beginning with and what you're ending with. Moles of CO2. Now, this is an important idea. You've been taught in the previous chapter that 1 always goes by mole. And if you're doing a mole conversion, that is true. But in a stoichiometry problem, it's not 1, because we're relating based on these coefficients. So what is the relationship between carbon dioxide and water? For every 6 moles of carbon dioxide, everyone see the 6? For every 6 moles of carbon dioxide, we need 6 moles of water. So the ratio is 6 moles of CO2 to every 6 moles of water. Now this step has a special name. I have named this step, and so has your textbook, the mole ratio step. And this is the only new step in our stoichiometry problems, the mole ratio step. And this is the only time you can have a number other than 1 next to mole. Now you can have a 1, but you can also have any other whole number next to moles, which is new and different to you. Now, if you're looking at this and you're saying 6 over 6, that does reduce to 1 to 1, and yeah, you could reduce it, but I'd rather you not. Let's just go ahead and work it out. Now, what happens to moles of water? We have moles of water here and moles of water there. Those cancel, and so we're left with moles of CO2, which is what we're asked to find. What is 5 times 6? Did you say 30? 5. I'm going to draw arrows with green arrows. Did you say 5 times 6 is 30? Did you say 30 divided by 6 is 5? You are correct. And so our answer is 5 moles of CO2. Now, could you have done this without writing that down? Yes, you probably could have, because the coefficients were 6 over 6. What if it was 6 over 2, or 6 over 5, or 4 over 11? Not necessarily, which is why I want you to write it out, okay? So on this one, yeah, maybe you could have gotten it worked out without writing it out, but it's nice to write it out because it also shows you what's going on. What we're doing is we're using our ratio of moles of water to moles of CO2 to find out how much CO2 will react with that initial water. Let's go to a second example. Same reaction. This one's much longer problem. How many moles of glucose can be produced when 6 moles of carbon dioxide react with excess water? Hint, excess water means more than enough water. The amount of water is a non-factor. That means we've got way more water than we could ever use up, so we don't even need to think about it or consider it. So let's write down what's given. 6.0 moles of carbon dioxide. And then we're going to draw a bracket. On the bottom, I'm going to put moles of carbon dioxide to cancel. I'm always going to do that. If you can just remember that, then you're well on your way to acing this. Now on the top, we're asked to find moles of glucose. So I'm going to put mole of C6H12O6. Now I'm going to go back and look at my reaction. If you go back to your reaction, for every 1 mole of glucose, you need 6 moles of CO2. Ha! So 1 mole of glucose, we need 6 moles of CO2. Remember that this is the mole ratio step, and this is the step that you're going to have in every single stoichiometry problem. You're going to have a mole ratio step in every single problem. All right, moles cancel out. 6 times 1, 6 times 1 is 6. 6 divided by 6 is, did you say 1? If you said 1, you are correct. We would make 1 mole of glucose. Again, yes, the numbers are easy on this problem, but it's important to start with easy numbers. It's important to start with easy numbers so you can get the ideas, and then we'll work with more complicated numbers. All right. Number 3. Now this one's different. I want to point out that this one is different right away because we're not asking for moles. We're asking for mass of carbon dioxide. So that's going to be something different. So let's write down what we're given. We're given 3 moles of water. And we're going to draw a bracket. Now this one's going to be 2 brackets. I want to go ahead and give that away now. I'm going to start by writing moles of water. Now, we're trying to end with mass of carbon dioxide, but first we need to convert to moles of carbon dioxide. I'm going to write you some steps after this, so if you're a little bit confused about where to go, I'm going to write you some nice steps. And if you're nice in class, I'll show you the stoichiometry mole map, which is helpful for a lot of students. So we're at moles of water. We want to get mass of carbon dioxide. The first thing we need to do, though, is find moles of carbon dioxide. So I'm going to put mole of CO2 on top. If you remember our reaction, it was a 6-to-6 ratio. For every 6 moles of water, we need 6 moles of carbon dioxide. That's cool, but we need to finish this. So now we're at moles of CO2. Did the problem ask for moles? Say no. The problem asked for mass of CO2, so we need a second bracket attached. There will be those students who like to stop and write down the number in between, but I'm not a big fan of that. I'm going to put moles of CO2 on bottom, and we're trying to find mass. What unit is mass in? Grams of CO2. Now, you should see that this is just converting moles to grams. This is moles to grams. This is moles to grams. That's just a simple basic conversion. 1 mole of carbon dioxide, 12 plus 2 times 16 is 44.0 grams. Moles of CO2 cancels out. So we're going to do 3 times 6 divided by 6 times 44. 3 times 44, 120. 3 times 40 is 120. 3 times 4 is 12. You get 152 grams. I don't have a calculator handy, so I'm just going to estimate 152 grams of CO2. No, I messed that up. That's not 152 grams. Back. I think it's 132 grams. Excuse my mistake. Alright, so now, that was our first reaction that wasn't just a single one little step. It was 2 steps. I'm going to check my time here because I don't want to run out of time. How much time do I have? 13 minutes. So I've got just enough time to write the steps and do some more examples in part 2. So let's add a step. So what are the stoichiometry steps? I've only got 1 minute, so I have to hurry. Step 1 is going to be convert to moles. What if you're already in moles? Skip step 1. Step 2, use the mole ratio to convert to what the problem asks for. Use the mole ratio. Remember, the mole ratio will always be moles over moles. Step 3, convert to appropriate unit. Sometimes you'll just finish in moles. Sometime a problem like the last one will ask you to finish in grams. Now, I want to make this very, very big point. This step and this step are the same as they've been for ages since we've been doing mole conversions. The only thing that's new in this process, is this mole ratio step. Everything else is the same old mole conversions and whatnot. Okie dokie. That's the end. Thank you for listening.